Okay. No Star Wars shirt today. I got my Cerritos College Falcon shirt on. Had to meet with my boss, so had to get my spirit on. It's good. Okay, let's jump into R4 and R5, shall we? Okay, R.4 is a slope and linear function. So this really is just a review of basic algebra. Okay, very basic. So R4 is slope and linear functions. Okay, slope and linear functions lines. Okay, let's talk about horizontal lines, horizontal and vertical lines. Okay, horizontal and vertical lines. Okay, what's a horizontal line? Well, horizontal line, okay, it looks like this. Y equals B is the equation of a horizontal line. Okay, so Y equals B is the equation of a horizontal line. Okay, so it's also called a constant function, aka constant function. Okay. Okay, and so what does this look like? Well, if we have a graph, X and Y, and we're up here at B, well, it's the line. Oops. Yeah, whatever. It's the line that goes through B. Like that. That's better. Okay, it's the line that goes through B. So Y equals 2, horizontal line that goes through 2. Okay, Y equals negative 2, horizontal line that goes through negative 2. Okay, so let's look at a graph of this. Example 1, graph the line Y equals 4. Okay, so where's the line Y equals 4? Well, we go up 1, 2, 3, 4, and then we would draw a line through 4. I want to do that. So this would be Y equals 4. Okay. Alternatively, what is the vertical line? Well, the vertical line is a vertical line is of the form x equals a. Okay, so this is x equals a. Vertical line is of the form x equals a. Oh, okay. So if we're out here at a, oops, we're out here at a, then that's the line x equals a. Okay, this is not a function. Okay, so x equals a is not a function, but it is still a line. Still a line. It's the only line that's not a function. Okay, it's the only line that's not a function because we have repeated domain values. We actually have every single point in this line is a repeated domain value. Right? Every single point on the line is a repeated domain value. Okay, so let's see what this graph has. Number 2. Let's graph the line x equals -3. Okay, so let's graph that line, x equals -3. So every point on this line is going to have an x value of -3. So if I did -3, 1, -3, 2, -3, 0, -3, -3, okay, all of those points are on the line, okay, on the line. X equals -3. Oh, okay. So where is x equals -3? 1, 2, 3. Okay, and so we go 1, 2, 3, 1, 2, 3. Oops, that's a little bit too long, too far. Okay, and so where are all these points? Well, at -3, 0, I'm here. Okay, at -3, 1, I'm here. At -3, 2, I'm here. At -3, -3, I'm down here. So these are going to be the points -3, 2, -3, 1, -3, 0, and -3, -3. Horizontal line. Okay, let's look at a definition. You're welcome, Adam. Okay, definition. The variable y, okay, the variable y, no, I haven't taken attendance yet. Thank you. Okay, the variable y varies directly with x, okay, if there is some positive constant okay, varies directly with it if there's some constant k, okay, so that y is directly proportional, to x. Okay. So y and x are directly proportional. What does that mean? It means that they create a proportion, y equals x is equal to k. Okay, so the proportionality constant is k. Y and k are always proportional to each other. Okay, no matter what I have for my y value, that's going to be always proportional to my x value. So y over x is always going to get me the same value. For example, the proportion 10 over 2 is equal to 5 over 1, right? So in this case, if I had the points 2, 10, and the point 1, 5, okay, that means that the points on this line are going to vary directly because they're proportional to each other, right? So a way to see that is that this is just a slope of k for a line. The proportionality constant is just the slope. How do I know that? Well, let's multiply both sides by x. And what do we get? We get y equals kx, and so k is the slope. Okay, k is the slope. Okay, let's do an example with this. Okay, number 3, the weight m in pounds of an object on the moon is directly proportional to its weight on Earth, right? To its weight E on Earth. Boom. Okay. An astronaut did I spell that right? Yep. Okay. An astronaut who weighs 180 pounds, on Earth will weigh 28.8 pounds on the moon. Okay, on the moon. A, find an equation of variation. Okay, let's find an equation of variation. Okay, so we want to know, okay, y equals kx. Okay, we could say, this is going to be maybe E equals K times M, right? So to put it in different variables, this is the Earth weight is going to be equal to some proportionality constant times, okay, times M. Okay, so they're going to vary directly, right? So when your weight goes up on Earth, your weight goes up on the moon. When your weight goes down on Earth, your weight goes down on the moon. Right? Okay. So what we need to do here is we need to solve for K. We need to solve for K. Okay. So let's do that. Okay. So we have 180 pounds on Earth is equal to K times 28.8 pounds on the moon. We'll just divide by 28.8. And we get K to be equal to what? Okay, 180 divided by 28.8. Okay, so we're getting 6.5. Thank you, Chris. 6.25, exactly. 6.25. So you weigh 6.25 times more on Earth than you do on the moon. Right? Okay. So what is the equation or the conversion factor here is E is equal to, your weight on the Earth is equal to 6.25 times your weight on the moon. Okay. So there's my formula. Okay. So part B, find the weight on Earth, or sorry, on the moon of someone who weighs 120 pounds. Okay. So find the weight on the moon of someone who weighs 120 pounds. So how are we going to do this? Well, we're just going to plug in their Earth weight and count and try to get their moon weight, right? So E equals 6.25 M. So we're going to plug in the 120, 6.25 M, and then divide by 6.25. Okay, and we get what? What's their moon weight? How much are they going to weigh on the moon?
19.2.
19.2. Thank you very much. Who was that?
Me.
Mario. That's me. Me Mario.
Yeah.
It's a me, a Mario. Sorry. Like you've never heard that, right?
Yeah.
You set yourself up, bro. Okay, that's all I can say. Okay. It's a me. It's a me, a Mario. Okay. I'm Luigi. Okay, 19.2. Anyway, we're huge gamers at in our family. So huge. We literally have 6 consoles, 8 if you count the handheld ones. So yeah, we have two Xbox 360s. We have PS4. We have 2 Nintendo Switches. We have a Wii U, we had 2 Wiis, but I got rid of those. Okay, so we had 2 Wiis, 1 GameCube. We have 2 Switches and 2 360s and 2 Nintendo DSs. So each child had their own DS, 360, and Switch. Yeah, and the only reason why they had each child had each of those, was because I wanted to end up with 2 children at the end of that adolescence instead of just 1. That was the reason for that. Okay, because they were literally gonna kill each other. Okay, there were controllers thrown at each other, and at that point it was like, I'd rather pay for the extra technology than for a hospital bill, because the hospital bill was going to be a lot more. So that was just how that was going to work. But anyway, I digress. But I've been playing video games since I was 5 years old. My father bought me a Nintendo. My father bought me a Atari 2600 when I was 5, and I was hooked. For the rest of my life, I was hooked. As soon as I saw Pitfall and Adventure and combat, I was hooked. Boom, that was it. And then I got my little gray box in 1986, and I was super hooked. So anyway, yeah. So, and then they're like, what skill can video games teach you? Blah, 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 blah. And look at this. Now we're COVID and everybody's having to learn online. So who's the fool now? That's what I'm saying. Who's the fool now? Okay. Anyway. Makes you think. Okay. Definition. Okay, a linear function is any function. Okay. Oh, I forgot to put my mask on. Sorry. I live in Orange County, so we're trying to make sure that nobody else ever gets sick again in Orange County, so we can go back to school. So make sure I put my mask on. I don't want you guys keep your germs and I'll keep mine. Okay, so just anyway. Sorry, I can't breathe. Okay, a linear function is any function, okay, that can be written in the form y equals mx plus b, where m is the slope. And b is the y-intercept. and 0, comma b is the y-intercept. So 0, comma b is the y-intercept. Okay, blah, 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 blah. Okay, let's go on to example number 4, right? We do example number 4? Sure. Okay. Okay, find the slope and y-intercept of the following equation. Find the slope and y-intercept of the following equation. 2x minus 4y minus 7 is equal to 0. So we want to basically solve this for slope-intercept form, okay, which is what this guy is. Slope-intercept form. Slope-intercept form, okay? And I know I'm probably not teaching this to anybody for the first time in their life, possibly, but I do need to make sure that we're all on the same page going into chapter 1. Okay, so I don't want any gaps, no excuses for any gaps in understanding. Okay, so let's find the slope and y-intercept of this thing. Okay, so I want to solve for y. Okay, so the first thing I want to do is I want to get rid of this this 7. Let's move this 7 to the other side. Let's add 7. Okay, so 2x minus 4y equals 0 plus 7, which is 7. Okay. Okay, and then the next thing I want to do to solve for y is I want to subtract off the 2x. Okay, subtract off the 2x. So this becomes negative 4y equals, I could go 7 minus 2x, but I know that the x has to go first, so I'm going to go negative 2x plus 7. Write it like that. Okay, maybe I won't skip steps. 7 minus 2x. There you go. Okay. But again, in the next step, I want to make sure that I bring that negative 2x over. Negative 4y equals negative 2x plus 7. Okay. Now what I want to do is divide through by negative 4. Now I can divide both sides by negative 4. And then, is that me or you? That's somebody. Someone else. I thought I muted all you people. Maybe not. Where's their mic on? No one now. They're embarrassed. So they turn their mic off. That's good. Okay. Okay. So we got y equals, okay, negative. It's okay. It's okay. It's all good. Okay. Y equals, now I can break this up into negative 2x over negative 4 and 7 over negative 4. Why can I do that? Why can I go negative 2x over negative 4 plus 7 over the heck's going on?
Would that just be half x plus 7 over 4?
Say it again?
You simplify that, would it just be half?
Yeah, we're gonna simplify further. Okay, definitely. Plus, I need to stop sharing for 1 second. This thing is lagging for whatever reason. Okay, let me stop sharing and then I'll go back to and then I'll start sharing. Oh. Come on, dude. Be nice to me today. Did it just freeze? It just froze. Oh, you are a pain in the butt. Yes, go away with your bad self. Okay. That's weird. Okay. So let's try to unfreeze this thing. Is it going to unfreeze or not? Yep, it's going to unfreeze, hopefully. Sorry, technical difficulties. 1 second. We're up and running again. I just had to reboot my system. So I don't know why it's still sharing my screen, because it shouldn't be sharing my screen, because I just shut my entire system down. But whatever. Maybe it's a Zoom issue. Who knows? It's frozen there. Okay. There we go. Finally. Caught up. It's like, you're not showing your screen. So now where can I plug this thing in so that I can actually get it to run? That is a good question. I know where I can plug it in. Right here. There we go. Perfect. Yay. Makes me happy. Okay, so let me log back in. Make sure this thing doesn't go away again. Okay. I bought this very expensive tablet, and it likes to overheat. So it wasn't for a long time. I know it's overheating again. I think it has something to do with the fact that it's like 100 degrees outside. So it's overheating inside. So, you know, it's like, they're like, oh yeah, you know, let's go teach in California. I never said, let's go teach on the surface of the sun, because that's like how it feels outside. It's been like 3 weeks. I'm like, come on, just give me a breeze. Give me something. Just throw me a bone. Okay, what we got here? I'm back. I'm back, people. Back. Continue. Okay. Let me see if I can share my screen again. Let's share it. Boom. Yay. Nice. Okay. Okay, here we go. Okay, so we have negative 2x over negative 4 plus 7 over negative 4. Okay. And so we really want to ask ourselves, well, why can we do that? Why can we break it up like that? Right? And it comes to us with fractions, right? So say I had 1/4 plus 2/4, right? So what's 1/4 plus 2/4? Oh, isn't that 3/4? Right? Wouldn't that be 3/4? Wouldn't this be 3 over 4? Right? So what I could do is I could actually rewrite this though as 1 plus 2, 1 plus 2 over 4, right? And isn't that the same as 1/4 plus 2/4? Isn't that the same thing? Right? Does that make sense? So we just broke it up. We broke it up into its common denominator. Okay. Does that make sense? And we apply that over here. So now we're going to go y equals 1/2 x. I'm just going to rewrite it like that. 1/2 x minus 7/4. Okay. So what's the slope? Well, the slope is equal to 1/2. And what's the y-intercept? Well, it's plus a negative here. Plus a negative, this is going to be b. B is a negative, so the y-intercept is located at 0, -7/4. Okay, so that's the slope and y-intercept of that function. Okay, now what's really going to come in handy is what we're going to talk about next, which is slope, point slope form. Okay, so y minus y1 equals m times x minus x1, okay, is called point slope form of a line. Okay, and this really comes to us from the slope formula. What's the slope formula? Slope formula is y2 minus y1 over x2 minus x1. And what happens when we multiply both by x2 minus x1? Okay, we get these two to cancel out, and we're left with y2 minus y1 equals m times x2 minus x1. And if we let x2, y2 vary, and so we just let it be x, y. So we let x2, y2 vary, allow that point to vary. Okay, on that line, we have a point, and then we have another point, and we're going to let that point vary with respect to this thing called slope. So we're going to say that we have point x1, y1 here, but the second point is going to be allowed to vary along this stuttering, along the trajectory of going over or going up by a certain amount and then going over by a certain amount. And that's called the slope, right? Remember the rise over the run? Okay, so we get the rise over the run, and that's always constant. That's always constant proportion. And so if we just say, I'm stuttering again. Okay, if we just allow the point to vary, we just let it be a generic x and y, every single point that has every single point on this line is going to have the same slope. Okay, and that's going to create the line that we're looking for. And so we just, instead of letting it be y2 and x2, we just let it be x and y, and that becomes the point slope form of a line. Okay, so point slope form of the line. Okay, that's the point slope form of the line. Very helpful. This is extremely helpful to us. Okay. Okay, so we want to do number 5 here. Let's find the equation of a line okay, find the equation of a line with slope 3 containing the point -1, 5, or -1, -5. Okay, and that's it. Okay, so find the equation of the line. Well, we're going to use point slope form. Why use point slope form? Because we have what? We have a point and we have the slope. Right? We have a point, we have the slope. So use point slope form. Very original name. Okay, it is what it is. It is called exactly what it is. So we're given a point and we're given the slope. So we're going to say that y minus y1 equals m times x minus x1. So y minus, what's y1 in this case? Well, it's -5. That's my y value of my point. Okay, this point is x1, y1. x1, y1. That's that point there. Okay, and so this is y minus -5, that's the y value, equals 3 times x minus, okay, -1. Okay, so I'm going to simplify this and clean it up. I'm going to actually put it into slope-intercept form. This becomes y plus 5 is equal to 3 times x plus 1. I'm going to distribute. I get y plus 5 equals 3x plus 3. And I'm going to subtract 5. And I get y equals 3x minus 2. Y equals 3x minus 2. Okay. Okay. Let's keep going. Let's keep going. Just keep swimming. Just keep swimming, swimming, swimming. What do? We swim. Okay, slope formula. Okay, what's the slope formula? Slope formula, m equals y2 minus y1 over x2 minus x1. Okay, for 2 points on a line, x1, y1. Could you scroll back up a second? Sure. There you go. Okay, x1, y1. Okay, x2, y2. Okay, sounds good. Slope formula. Okay, for 2 points on a line, right? Okay, so number 6. Find the slope of the line containing the points -2, 6 and -4, 9. Okay, find the slope of the line containing the points -2, 6 and -4, 9. Okay, -4, 9. Okay, so let's see what the slope of that line is here. So m equals y2 minus y1 over x2 minus x1. Okay. So this is going to be, what's y2? What's y2 in this case? What's my second y value?
9.
9.
Yes, 9. Thank you. Thank you, Darlene. Thank you, Mario. Thank you, Christian. I don't know who else said anything. I forget. There was a female voice there at some point, I think. Okay, so 9. Yeah, 9. Okay, 9. What's y1? What's y1?
6.
6.
6. Very good. Okay, 6. Yes, don't say it like it was some other word because that's inappropriate. Okay, it's 6. Okay, so x2. What about x2? -4. Thank you, Paulina. Okay, -4. And then x1?
-2.
Yep, -2. Very good. Thank you, Gabriel. Okay, -2. Okay, so now we're going to add and subtract these. So this is 9 minus 6, which is 3. 4, -4 plus 2, which is going to be -2. So this is -3 over 2, right? Okay, so that's the slope of a line through those 2 points. Okay, okay, number 7. We're going to finally get out of the boring stuff, okay? Trust me. Okay, the reason we have to do the boring stuff is because you got to walk before you can run. This is actually crawling. We got to crawl before we can walk. And then we got to walk before we can run, right? So that's the idea here, is we just need to make sure that everybody knows how to crawl first. Okay, so can you crawl? Yes, we can. Okay, that's a homage to Bob the Builder, but whatever. My references are like dated. Okay, I date myself a lot, but that's because nobody else will. So it's just the way it works. I'm just kidding. Okay. Okay, number 7. Find the average rate of change. You guys are a tough crowd today. Is it just too hot out? Or is it like, it's literally 74 degrees in here. And I don't like it 74 degrees because I'm right next to this window that's very hot. And it beats down on me all day long. And I don't have my thermostat set to 74. I have it set to 70. But for whatever reason, it won't go any lower. I have the air on full blast in the house, and it won't go any lower than 74. So
You're cursed with room temperature.
it is sad. It's sad. Like that's sad. Like I'm literally sweating here. So maybe I just need a new air conditioner. I don't
I
know.
think my room's like 60 degrees and I'm complaining.
There you go. Exactly. So it won't get any cooler in this place, but that's because of the time of day. Because this side of the house faces the west, right? Faces the beach. So at this point in the evening, it's this. I'll open this for you. Okay, you can see. Where's the sun? Oh, it's almost down. It's almost down. But it beats the heck out of me. So it's like almost down. Keep going, bro. Keep going. I got about 5 more minutes of you beating on me. And that's it. So go away. Go away. I'm complaining now, but you know, toward November, I'm gonna be like, it gets dark too soon. This sucks. So I'm never happy. It's just whatever. Whatever. You just ignore me. Ignore my ramblings, because that's what my kids do. They're just like, there goes Dad again on his little rant. Whatever. Okay, find the average rate of change. Okay, the average rate of change, okay, of billions of dollars okay, per year if in 2000 there was 3.311 billion dollars. Okay, billion dollars. And okay, stop, be kind, go away, go away, go away, go away. There you go. Okay, $3.311 billion, and in 2013, there was $4.8 billion spent on cancer research. Okay, so what we want is something called a unit rate. What's the unit rate here? What's the unit rate? What's the average rate of change per year? Right, that's the unit rate. right? So what's the average rate of change per year? How much was spent, how much monies were spent per year on average? Well, that's a slope formula. Okay, m equals y2 minus y1 over x2 minus x1, right? Okay, so what do we got here? Well, we've got these points here. The x was 2,000, and then we have 3.311. And then the other point was, the y was 3.311. The other point was 2013 and 4.8. And so we got to find the average rate of change here, which is just the difference between the monies and the difference between the years. So m is equal to the difference in the monies. This is 4.8 minus 3.11, or sorry, 3.311, all over the difference in the years, which is 2013 minus 2000. Now you could have done that in your head. You'd be like, well, of course it's over a 13-year period. So we are taking, and if we subtract this 4.8, okay, minus 3.311, we would get 1.489. We divide by 13, we would get 0.1145, okay, billion dollars per year. Billion dollars, okay, $billion per year. Okay. The thing is, though, that we don't really think about this as $0.1143 billion. If I wanted to change it to millions, I would just move the decimal over 3 times, and then I could change it to millions. This is $114,500,000, okay, per year. Okay. So that's how much was spent roughly each, or that's the rate of change, the average rate of change. So what is the average rate of change? That's the average amount that it's going up by. Okay, that's the average increase. So on average, on average, we are increasing by by the amount that we're spending on cancer research by $114,500,000 extra dollars every year. Okay, so we're say that our base is $3 billion. Well, we add 114 million to that each year, and then you're going to get at the 4.8 after 13 years. Okay, if that makes sense. Hopefully it does. Okay, let's do a business application, because that's what this is all about, right? It's all about the business. Let's get down to business. Down to business. Okay, the total cost function. Okay, total cost function can be modeled by the C of x, which is equal to the variable costs plus the fixed cost. Okay, so we've got the variable costs and the fixed costs, right? The variable costs and the fixed costs. Sure. Okay. Okay, so what are the variable costs? Well, the variable costs are like how much it's going to cost to produce X items. Those are your variable costs. Okay, variable costs, cost per item. Cost per item. Okay, what are your fixed costs? Your fixed costs are just your overhead. This is just the cost of business. Okay, that's just the cost of business. So say I go out and I buy a machine to make widgets, right? So I go out and I'm going to make some widgets, and I buy a machine, a $10,000 machine, okay, to buy my widgets, to make my widgets so I can sell them, right? Well, is that a variable cost or a fixed cost? That machine that I just bought for 10 grand, is that a variable cost or a fixed cost?
Fixed.
It's a fixed cost. Yeah, it's a fixed cost because it's not a per item cost. I mean, I could make tens of thousands of items using this machine, right? So it's a fixed cost. So I'm going to say that C of X here is equal to a fixed cost of $10,000. Now, my materials cost, is that a fixed cost or a variable cost? My materials cost.
It's a variable cost.
Yeah, Mario says a variable cost. Aaron says variable cost. It's a variable cost, right? Of course it's a variable cost. Why? Because they per item cost. If I want to make my gold rings, right? Then I want to print off gold coins, whatever it is that you're making. You have to have some material to do that. So what would be the cost of the material? Okay, we'll say that we're making silver coins. Okay, not gold. Gold is too expensive. Okay, we're making silver coins, right? And so what's the cost of the material for each silver coin? Well, I'll just say that the cost is going to be $20 in materials to make these silver coins. And then I'm going to put them into a $10,000 coin press, and they're going to make some really nice coins. Okay, however, that $20 is per item. So that's going to be times X, right? Times X. X is the number of items I'm producing. So X is the number of items. 20 is the materials cost, which is a variable cost. And 10,000 is my fixed cost. Okay, so what we call this is my total cost function. This is the total cost function. Okay, find the cost of producing 400 coins. What is the cost of producing 400 silver coins? Okay, well, that's going to be C of 400. That's the cost of 400 coins is going to be equal to the material that I'm going to spend. Okay. Okay. Giselle says it's 18,000. Okay. Yes, it is. You're right. Very good. Giselle Lucero says it's 18,000 as well. Very good, Lucero. It is 18,000. Okay, so it's 200 times 4 or 20 times 400 plus 10,000. So what's this going to be? 8 grand plus 10 grand, which is going to be 18 grand. Okay, 18K. Okay, so those are my overhead costs. Okay, that's the cost of producing 400 coins. Okay, make sense? Okay, let's switch gears. Okay, R5. R5 is non-linear functions. Okay, non-linear functions. Okay. So what's a quadratic? Quadratic. Okay, what's a quadratic? Well, quadratic is a parabola. Okay, and it's anything that stops at x squared being the highest exponent. Okay, so like y equals x squared, okay, that's a parabola. Okay, that's a quadratic. Okay, now the quadratic has nothing to do, the reason this is named a quadratic has nothing to do with the fact that it's the second power. Okay, absolutely no idea, or no correlation between the fact that it's the second power and then it's a quad. Because when you think of quad, you think of four, right? Quad runner is 4 wheels. Okay, quadriplegic, 4 limbs that no longer function at their full capacity. Okay, quad is 4, then why is the second power, right? Didn't make any sense. Well, it has nothing to do with the fact that it's the second power. Mathematicians just named this a quadratic because up until now, all you had was lines, right? All we had was lines. And lines could only go through as at most 3 quadrants. Lines can only go through at most 3 quadrants. This is quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Notice that a line can go through at most 3 quadrants. However, a parabola can do what? It can go through all 4. Yeah, it can go through all 4. That's why it was called a quadratic back 2,000, 3,000 years ago. Okay, because it was the first shape that they graphed, and it went through all 4 quadrants. Like, oh, it's the first one that can do that. So they call it a quadratic. There you go. Okay. A little history of mathematics for you. Okay, there's actually a book, okay, that I have. Where's my book? There it is. Called, what is this called? It's called The History of Mathematics. Okay, it's the history of mathematics. If you're ever tired and you can't go to sleep, this is the book for you, right here. You take it and you just like hit yourself over the head with it. You're out. No, I'm just kidding. You start reading this stuff, and it's the most boring stuff in the entire world, and you're right out. It's God's gift to insomnia. Okay, it's basically 3,000 years of mathematical history, and you're good. It's like 15 minutes. You're like, oh yeah, Cauchy. Who's Cauchy? And why do I care? And you're like, oh. It says Cauchy, in one respect, was quite unlike Gauss. He leapt into print as soon as he achieved something. Perhaps this was one of the reasons that the chief characteristic of the 19th century mathematics, the introduction to rigor, is attributed to Cauchy rather than Gauss. Ooh, I mean, it comes off like, some steamy novel between these guys, Cauchy and Gauss. They're fighting for prestige. Whatever, who cares, right? They're all dead white guys anyway. Who cares? Just throw them in a vat. There you go. Okay, so whatever. Okay, anyway, so that's your little history of mathematics lesson. I have read through that book, by the way. It was a class I had to take in college, so it was fun. It was good times. Good times. Yeah. Good times. It was 2 o'clock in the morning reading that book, trying to cram for the exam. So it's good times. Good times. Okay. So what's the generic equation for a quadratic? Well, it is f of x is equal to ax squared plus bx plus c, right? So ax squared plus bx plus c. Okay, so a has to be greater than, if a is greater than 0, then it opens up. Okay, up, like a cup, right? Cup opens up like that. See, there's my quadratic. It's like a cup, right? Whoosh. Opens up. Cup, up, get it? Spicy. Okay, see what I did there? Okay, it's a cup, opens up, boom. Okay, this are the things I had to come up with when I taught middle school. They're like, I don't know. Middle schoolers are stupid. Okay. They'll do anything for like $5. They're like, I'm like, eat a booger for $5. Oh, okay. Okay. Jump off the roof for $5. Oh, okay. Go play on the freeway for $5. Oh, okay.
Make it 10.
They're dumb. So yeah. Just try it. If you have a little younger brother in middle school, you're just like, I'll give you $5 to do. But don't tell them to play on the freeway because they'll actually do it. They'll actually do it. So you don't. I'm not. Don't tell them to do that. Okay. They'll do it. Okay. So okay. Anyway, A is less than 0. Okay. What is this? This opens down. Okay. If it's negative, if A is negative, this opens down. Okay. Oh, like a frown. Oh, look at what I did there. That's like a frown. Okay. A little tear here. Frown. A frowning emoji. Okay. I'm crying because I spent way too many times around middle schoolers. That's me crying, going home, wondering what the hell I'm doing with my life, teaching middle school. That was me around 23 years old. So, yeah. Okay, frown, opens down, frown, frown. That's Professor Holtman right there, frowning. Okay, pondering the meaning of life and the existence of me teaching middle school for the rest of my life. That was not going to happen, I assure you. Okay. Yes. Okay, let's do some graphing here. Let's graph. Okay, f of x is equal to negative 2x squared plus 10x minus 7. The only good part about middle school was all the free food I got. That was it. Teaching middle school. I got a lot of free food. Want to know why? Because they weren't allowed to eat in my classroom. So, however, I did make one concession. And that is if they brought me the exact same thing, then they could eat in my classroom. So they were like, so if they wanted to eat a donut in my classroom, they had to bring me a donut. If they wanted to eat their mac and cheese in class, they had to bring me mac and cheese. So, and because they were stupid middle schoolers, they actually fell for it and they did it. So I got a lot of free food. So, good, because to supplement my low teacher income, that's what that was. Okay, like, yeah. Okay, anyway. Okay, so what are we doing here? We're graphing this guy, right? Negative 2x squared plus 10x minus 7. Okay, we want to graph this. Well, we can do something, and we can find the vertex here. We can find the vertex. The vertex of a parabola, okay, is at negative b over 2a, and then f of negative b over 2a. That's the vertex of the parabola. Okay, the vertex is at this coordinate. So if I want to find the vertex, I would just have to do negative b over 2a. Well, what's a, b, and c here? Well, a is negative 2, b is equal to 10, don't want you to forget that. Put that in your notes there. Okay. Okay. So negative 2. Negative 2 is a, b is 10. So what is this? This is going to be negative 10 over 2 times negative 2, right? So that is going to be 2.5. The negatives cancel out, I get 2.5. And then I have to figure out, well, what's 2.5 going to be here? Right? I can actually do this in the calculator if I want. So let me stop my sharing for a second. Let's go to the calculator. If it'll pull up at all. Is it going to pull up? Come on, Mr. Calculator, boot. Boot up. Boot it up. Boot it up, boot it up, boot it up. Okay. So what I can do, if I can move this thing. Come on, stop. Stop, behave. There we go. Okay, so what I can do here is I'm going to clear this. I'm going to graph this thing. Y equals, clear. Okay, y equals negative 2 x squared, okay, plus 10x minus 7. Okay, and I'm going to hit enter. And then I'm going to graph this guy. Okay, oops. Let's zoom out. Let's do zoom standard. Standard is just a box, 10 by 10 box. So I'm going to go zoom standard, and there's my parabola, right? What I like to do is find out, okay, well, what's the y value here on my parabola? I don't really want to have to. So what I do is I hit the trace button, and I say, well, when x is equal to 2.5, what's y? And it tells me, oh, y is 5.5. Maybe I'll make this bigger so you can see. This is bigger here. Come on, go. No, I didn't want to do that. I want the view. I want no, show large display. There we go. Okay, so now bring this over like that. Look at that. Nice. Okay. And we can see that when x is equal to 2.5, y is equal to 5.5. Right? When x is equal to 2.5, y is equal to 5.5.
Professor, if we do it by hand and we don't have a graphing calculator, would we just plug it into the function?
Function, exactly. You would just plug it into the function. Yes. Okay. You could actually pretty easily do that as well. Let's go back to this guy here. So let's go back here. So if you want to plug it in the function, you can. F of 2.5. Oops. I need to get rid of that. Are you kidding me? This is going to crash my system again. You better not crash my system again. Maybe that's what it is the stupid calculator is wanting to crash my system. Stop crashing my system, bro. Well, that sucks. Yeah, I'm not using that calculator anymore. It's not worth it. I'm gonna use Desmos from now on. It's not worth using the calculator. So anyway, you would get 5.5 here. Okay. Live and learn, live and learn. It's good that this is happening at the beginning of the semester, not the end. Okay. The calculator is a piece of crap. I'll find a different one to use. So, hopefully an older version. It's less buggy. Sign in again. Okay, at least I know what the problem is. At least I know what the problem is. Everything's working great up until I bring out the calculator. And then everything goes haywire. There it is. Am I back? I'm back. Again, with a vengeance. Screen, share the screen, boom, yay, share my screen, share my screen, please, share it. Share the screen. Okay, I'm sharing. I'm not sharing. I'm not Sharon. I'm Jason, but I am sharing my screen. So Karen, I'm not Karen either. So did you know they're actually handing out free food if you can prove that your name is Karen? You bring in your ID. People, there are restaurants that are giving away free food to people named Karen because they feel so bad about the way that name has been treated. I don't know. I still don't know what a male Karen is, or does one even exist? Like, what's the name of a male Karen? Is it Aaron?
Kyle.
What is it?
It's Ken.
It's Ken. Ken. Okay. Male Karen is Ken. And their son is Kyle. Is that right? Right? All the Kyles of the world, they have Karens and Kens as fathers and mothers. Right? So maybe? I don't know. Kyle was big last year. Right? Last year at this time, all the Kyles were going to invade Area 51. Remember that? Remember that? Woohoo! Yeah.
100 people went.
I went.
Did?
I went. Yeah, I was there.
How was it?
It was great. You want to see a picture? It was awesome. Actually, it wasn't. There was not much there. No, not many people went.
I was imagining it. Like I was thinking maybe it'd turn out like a Burning Man, but oh well.
Yeah. No. Well, it was a good. It was. My son wanted to go, so he was just an excuse for a road trip for me and my son to go to Vegas. That was it. So, like, oh, you're fine. Let's go to Vegas. Like, just an excuse to have a road trip with just me and my son. So, good times. So anyway, if we do plug this in, we get f of 2.5 is equal to, okay, -2 times 2.5. If you just want to do it by hand, you can. And then you would go plus 10 times 2.5 minus 7, and you come out with 5.5. If you plug that into a calculator, you get 5.5. I'm not using the calculator because it's just going to crash my system again. Okay? So equals 5.5. Okay. If I wanted to graph this, right, we know where the vertex is, and the vertex is at 2.5. So I'm gonna get some points around 2.5. Seriously? Tell me this isn't gonna work again. Oh my gosh. Hey, sorry, I'm so sorry for all the technical difficulties we're experiencing today. I don't know why my system keeps freezing. We're almost done anyway, so it's all good.
Do you have a upgraded router possibly?
I do. I don't think it's on my internet. Otherwise, both my systems would be going down, right? And both of my systems are hardwired into my machines. So I have no Wi-Fi issue because they're both hardwired. They're both Ethernet cabled in.
Oh,
It's not a Wi-Fi issue. It's an issue with my Surface Book 3, which I'm going to basically mail back to Microsoft. Tell me to get. Microsoft is notorious for pushing out hardware and software that's full of bugs.
oh.
That's fun. And then they're like, oh, well, once it's in the public domain, then we'll fix all of those issues with patches. Oh, okay. Sounds good.
Once they get funded for all the money to fix the issues.
Yeah, exactly. Okay, let's try this again. Last time. Hopefully, third time's a charm. Keep our fingers crossed and our toes, everything else. Okay, last try. See if this works. Okay, scrolling, that's a good sign. Okay, so we're gonna go X and Y. At 2.5, we already know it's 5.5. 2.5 is 5.5. Okay, at 2, we're gonna be at 5. Okay, if we plug this in, f of 2 is 5. At 3, we're gonna be at 5. Okay, so if I plug in f of 2, this is negative 2 times 2 squared plus 10 times 2 minus 7. Okay, and we get that to be equal to 5. Okay, if I plug in 3, I get the exact same thing. Why? Why would I get the exact same 3? Because it's a mirror image. Okay, at 2.5, 1, 2, 3, 4, 5. At 2.5, where am I at? Well, I'm at 5.5. I'm at 1, 2, 3, 4, 5, 6. I'm at 5.5. But then what? Then I go down because this is a vertex. That's going to be the minimum or maximum value. In this case, because it's a negative, it's going to be a frown, right? It's going to be a frown. And so it's going to open down. Open down because it's a frown. And so on either side, the nice thing about parabolas is they're symmetric. There's a mirror image on one side as the other. And so at 2, we're at 5. And at 3, we're also at 5. Oh, isn't that nice? Okay, what about at 1? At 1, where would we be? Well, we plug it in, we would get 1. At 1, we'd be at 1. And then at 4, we'd also be at 1. So at 4, we would also be at 1. And so we get this nice parabola. Okay, that nice graph. You know what I'm going to do, actually? I think I know what I'm going to do from now on. If I need to use the calculator, I'm not going to use my tablet. If I need to use the calculator, I'm going to use this bad boy here. Because I have a desktop that's super powerful. And so I'm just going to have to switch my sharing from now on. But I think that's all good. It's going to be okay. Okay. See? So hopefully you guys can see that. Hopefully you guys are good with that there. Okay, so I think we've come to a workaround for this. Okay, so yes. You just got to be smarter than the thing you're working with. With computers, it's getting there, where you're not going to be smarter than what you're working with. That's the scary part. Welcome to AI. Okay, so if I need to share the calculator, I'll just do it this way. Stop me sharing. Go back to this guy here. Okay. Okay, what do I want to do? I don't care about that. I don't care about you. I don't care about you either. Ooh, let's graph this guy. Okay. Let's do number 2 here. Let's graph. Okay, f of x is equal to 1 over x. F of x equals 1 over x. What's that going to look like? Let's graph f of x equals 1 over x. Well, if x is 1, then what's y? What's f of x? If x is 1, then what's f of x? It's 1, right? Okay. If x is 2, what's f of x? Well, it's 1/2. Right? If x is 3, then it's 1/3. If x is 4, then it's 1/4. You kind of see a pattern here, right? Okay, what if it's 0? What if it's 0? What if x is 0? What happens? It's undefined. You can't divide by 0. It's mathematically undefined. Okay, it's not allowed. We're not allowed to divide by 0. Anybody know why we're not allowed to divide by 0? Why it makes absolutely no sense? Okay, let's define it. Okay, why does it make absolutely no sense to divide by 0? Well, think about taking 6 and divide by 2. What do you get? You get 3, right? You take 6 of something and you give it to 2 different groups. You take 6 items and you divide this into 2 different groups, and each group is going to have 3 items, right? Okay. So dividing 6 and putting it into 0 groups. How can you take 6 items and put it into 0 groups? Well, this is only allowed with a ton of dynamite. Okay, this is only allowed with a ton of dynamite. Okay, it's the only way you're going to get something into nothing. Okay, so does this make sense? You cannot get nothing from something in mathematics. Right? You can't say, oh, I've got 6 items, I'm going to put it in 0 groups. You're like, okay, well, where'd all your stuff go? It doesn't make any sense. It makes no sense whatsoever. Okay? If you have a ton of dynamite, then you can do it. Okay, like on that show on Cartoon Network, Destroy, Build, Destroy. Remember that guy? Okay, remember that? Anybody ever watch that? Yes. Destroy, Build, Destroy. Yeah, that was a good one. That was a good one. I like that. Okay. Anything where things are blowing up, that's fun, right? Like that's why Mythbusters was so fun too. Like this gonna blow that stuff up. Boom. Jamie want big boom. Jamie want big boom. Okay, so undefined. What if I have a negative number here? What's going to happen here? Or what if I have a fraction? Let's try a fraction first. Fraction. What if I have 1/3? What's the reciprocal of 1/3? What's 1 over 1/3?
3.
Yeah, it's just 3. Thank you. Thank you, Jess. Thank you. I think it was 3. Who said what? Brianna. Yes, thank you. Okay, it should be 3, right? So we're getting the opposite. And we could do negatives on all these too if we really wanted to, right? We could do negatives of those. So what is this going to look like when I graph it? Well, At 1, I'd be at 1. At 2, I'd be at 1/2. At 3, I'd be at 1/3. At 4, I'd be at 1/4. At 1/3, I'd be at 3. 1/3, I would be at 3. And so what this is this curve here. Okay. It's a really bad curve. Let's try it a little bit nicer. Oh my gosh, why is it? I swear I'm not doing that. I'm going to rework this. Okay. 1/2, 1/3, 1/4. At 1/3, we're at 3. And so we get this guy there. Okay, and then we get the mirror image of this rotated 180 degrees in the third quadrant. Okay. So same thing, which is negative negatives. -1 is -1. Okay, so that's that function there. That's f of x equals 1/x. It's a hyperbola rotated on a 45-degree angle. Okay. You know anything about hyperbolas? Maybe you don't, maybe you do. Doesn't really matter. Okay, so we've got this one. Okay, so this f of x equals k/x is called inverse variation. Inverse variation. Okay, inverse variation. Why? Because remember we had y equals kx was direct variation. Okay, and the way that direct variation works is if this goes up, right? If that goes up, that goes up. If my input goes up, then my output goes up. Because all I'm doing is multiplying by a constant. If my input goes up, my output goes up. But in inverse variation, that doesn't work like that. If I have y equals k/x, then if x goes up, what happens to y? As x goes up, as we divide
Down.
by a bigger number, what happens to y?
Decreases.
Go down.
Yeah, it goes down, exactly. It decreases, thank you. Okay, it goes down, decreases. Okay, as x goes up, y goes down. Okay, so this is inverse variation, inverse variation. Okay. Okay, let's look at some common parent functions. Okay, some common parent functions. Let's look at this guy here. F of x is equal to absolute value of x. This guy is my absolute value function, and it looks like this. It's a v. Okay, it's a v. It's a line, but instead of the line going like this, which is what would be y equals x, right? What are we not allowing? We're not allowing any negatives, right, as our outputs. We're saying that all of these negatives do what? They get turned into positives. Okay, and so we can actually write this as a piecewise function. We could say that f of x equals absolute value of x, okay, equals, okay, it equals negative x. That's the slope of this line here. I'll call this piece A and piece B. So piece A is negative x. The slope of that is negative x for x less than 0. If x is negative, then it becomes a negative x, right? Because what's a negative times a negative? Isn't that positive? Right? Isn't negative times a negative positive? So if x is -3, say x is -3, then what do I want to do with that? Don't I want to make it the opposite, 3? How can I do that? Wouldn't I want to multiply by a negative? Yeah. And then it's x, it's just x if it's positive or 0. For x is greater than or equal to 0, it's positive. Okay. If it's positive, we don't have any issue. If it's negative, we have to multiply that value by a negative to make it positive. Okay, so that's why that works. Okay, what's this guy here? This is called the square root function. What does that guy look like? Well, he's a parabola tipped on his side, but I've only got the first quadrant because I can only have positive x values and positive y values. I'm only allowed positive x's and positive y's. If I allow negative x's, I get imaginary numbers, and I don't want to deal with that. So what does this look like? It looks like this. Okay, that's the square root function. Okay, what's this guy here look like? 2 to the x power. That's called an exponential, and we're going to talk a lot more about that on Thursday. This is exponential. I'm just going to briefly show you what this looks like. If x is 0, what's anything to the 0 power? What's anything to the 0 power?
1.
1. Thank you. Does anybody know why? Anybody know why it's 1? 2 to the 0 is 1.
It's just the law. I don't know actually.
You don't know actually?
I know that it's 1, but I don't know
Yeah,
why.
but why is it 1?
I don't know.
No? No ideas? Okay, so if we look at this, right? If we look at 3 times 3 times 3 times 3 over 3 times 3 times 3, right? What is that going to reduce to? What's that going to reduce to? Isn't that just going to reduce to 3? Does that make sense? Yeah?
Yes. Yeah.
So we could say that this is 3 to the 4th over 3 to the 3rd is 3 to the 1st. Is that right? Does it make sense?
Yes.
What if we did this? We did 3 times 3 times 3 times 3 over 3 times 3 times 3 times 3. What if we did that? What's that going to be?
A 1.
Equal 1.
What's 1?
But isn't this really 3 to the 4th over 3 to the 4th? Which is what?
3 to 0.
3 to the 0. So that's why it works. That's why it works. So if we do 2 to the 0, that equals 1, right? So at 0, we're going to be at 1. This is the point 0, 1. When x is 0, y is 1. I'm going to get rid of my 3's here. Okay. When x is 0, y is 1. Okay. When x is 1, what's y? Well, it's 2. When x is 2, it's 4. When x is 3, it's 8, and so forth and so on. And so what this looks like is this. Oops. Okay. So there we go. That's my exponential curve, right? My exponential curve. What's the base? The base is 2. Okay. So it'd be like investing $1. Be like investing $1 at 100%. Okay, that means that I'll lend you $1, but at the end of the year you got to pay me 1 back. I'll lend you $1 today, but at the end of the year you got to pay me 1 back. And if you borrowed my money for 1 year, okay, you would end up with owing me $2. You end up borrowing my money for 2 years, you'd end up owing me $4. If you borrowed my money for 3 years, you'd end up owing me $8. Does that make sense? Okay, let's do our last problem. Okay, supply and demand function. Okay, supply and demand functions. Okay, as price increases, what happens to demand? As price increases, what happens to demand?
Decreases.
This
Demand
Decreases.
decreases. Thank you.
It's
Yes.
inverse.
Decreases. As price increases, demand decreases. Okay, that's inverse variation, right? Inverse variation. Like, you know, it's like as the price of my Starbucks, which I don't really go to Starbucks. I don't drink coffee, which is really a problem. I wish I could drink coffee, but I can't drink coffee because it tastes like crap. And nothing that I do ever makes it taste better.
Acquired taste.
My palate it tastes bitter, and I like things that taste sweet to other people taste really bitter to me. So it tastes like poison to my tongue. For whatever reason, I got way too many of those bitter taste buds and not enough of the sweet taste buds. And so, like, alcohol tastes like poison, and coffee tastes like poison. So the whole back of my tongue, okay, is full of these bitter taste buds. So I can't drink coffee. So I try to drink the hot chocolate at Starbucks, but that too is still too bitter. Because all they do is they're like, oh, we're just gonna put a couple pumps of mocha and then put it in milk. And then I'm like, dude, I still can't drink this. So you know what I get when I go to Starbucks? I get a vanilla bean frappuccino. That's it. I can't. That's all I can drink at Starbucks is the vanilla bean frappuccino. Because why? Because it just tastes like a milkshake. That's it. So might as well just go to Carl's Jr. and get my milkshake instead of going to Starbucks, paying $5 for a drink.
It's lucky you're not lactose.
I'm not. My son is, which I feel really sad for him. So he's a soy boy. So he drinks his soy milk. Yeah, he's a soy boy. So as price increases, demand decreases. Okay, as price increases, demand decreases. Okay, so again, going back to the Starbucks coffee, okay, if I had to pay $10 for a cup of coffee, that would suck. First of all, I wouldn't pay it because I don't drink coffee. Okay, and you wouldn't even want to see me on coffee because I'm hyper as it is. So it'd be like, you know, a squirrel on like speed, right? So no, that's not gonna work for me. So I would go to sleep if I drank like a few cups of coffee. I'd go to sleep in like 3 days. So it's just not gonna work. But if I was a coffee drinker and I wanted to go out and pay $13 for a cup of coffee from Starbucks, which I would have to mentally be insane to do, how many of those cups of coffee do you really think I'm going to purchase throughout the year? I'm not going to purchase many, right? Why? Because price is too high. Demand is going to be super low on your $13 mocha frappuccino with whip, half calf decaf, whatever that means. Okay, so you can get you can get a lot of those chinos, but it's at $13 a glass. Okay, at $13 a cup, forget it. Okay, nobody's going to be walking through your door. So as price increases, demand decreases, but what happens to supply?
Supply increases.
Yeah, exactly. Supply increases, right? Because why? Because I can't get rid of these cups of coffee. Supply increases. Right? Nobody wants to buy my coffee because it's $13 a cup. Oh, you can either reduce your price or you can go out of business. Right? Okay, supply increases. So price and supply vary directly, but price and demand vary inversely, there's an S there, inversely, okay, and supply and demand vary what? Supply and demand vary what? Directly or inversely?
Inversely.
Inversely, exactly. Okay, as demand goes down, supply goes up. As demand goes up, supply goes down. Okay, which is kind of interesting. Again, my family, we're huge gamers, right? And so Nintendo actually manipulates the supply and demand curve extremely well. That's why they're a multi-billion-dollar corporation. Okay, so they manipulate to the nth degree the supply and demand of their various IPs, right? And so what they do is they will reduce their price initially for all of their IPs so that you're able to come in on the ground floor, and then eventually like they're in the volume business, right? So say that a Nintendo Switch, you know, cost them, I don't know, $250 to make, okay, and they sell it for $300, right? So say that it cost them, probably doesn't even cost them that. But say that it cost them $250 for them to make a Nintendo Switch, and then they sell it for $300, right? Whereas, okay, they could have initially sold that thing for $400, but their business model is a volume model. It's not a, you know, I'm going to make X amount of dollars initially. So they want to, Nintendo has always reduced their price point to the point where they want everybody in the world to be able to own their console. So they're in the volume game. They're in the long game. They're playing the long game on these things, right? So they manipulate that supply and demand curve so that they give more supply, enough supply, and they lower the price to a price point where the demand is exponential, so that everybody can get on the ground floor. Because if they can sell you a Nintendo Switch for $300, they know that in the end they're going to make up all that money on the IPs that they're going to sell you later on. Okay, the Nintendo Online and the Mario Odysseys and the Breath of the Wilds and the Breath of the Wild 2, which I'm waiting with bated breath for. Give me my freaking Breath of the Wild 2, please, at some point.
Yes, please.
Exactly. Exactly. Come on, Nintendo. But this is why they make so much money. Because they know all about the supply and demand. Okay, so let's look at number 3 here. Okay, real quick. Okay, let Q represent the number of items produced okay, and X represent the price per item. Okay, so Q is the quantity and X is the price. Okay, so the demand is going to be equal to, okay, negative 25, okay, plus 50. Okay, negative 25 plus 50. Okay. Sorry, negative 25x plus 50. And that's the Q, that's the quantity demanded. The quantity demanded here is negative 25 plus 50. Okay, the supply is going to be X minus 25. The supply is equal to x minus 25. So this is the supply. That's the quantity supplied. So the quantity demanded is this function. Okay. So what is this going to look like? Well, what's negative 25 plus 50? Well, if I plug in 2 for x, that's going to bottom out here. Okay. 2 for x. Okay. So at $2, okay, that's too high. Okay. So let's do $2 here. Let's go up in 25-cent increments. 0.25, 0.50, 0.75, 1, 1.25, 1.5, 1.75, and 2. Okay, what does it mean? What does it mean that at what does it mean? What is happening at $2? That this thing would become 0. At $2, nobody's buying your product. Does that make sense? The quantity demanded at $2, nobody bought it. Okay. Now, what's the y-intercept here? The y-intercept is 50, right? So maybe I'll go up by tens here. 10, 20, 30, 40, 50. Obviously, this is not to scale, but it doesn't matter. Okay. Go away. Stop. I'm running out of time, people. Behave. Be nice to me. Come on. Come on. Don't do this. Don't do this to me. Okay. There we go. Okay. Come on. There we go. Okay, let's pull the ruler up here. Let's quickly draw our demand curve. Let's quickly draw our demand curve. I keep saying this and then I can't do it. Quickly draw the demand curve. There we go. Okay. Okay. So now let's quickly draw our supply curve. This is going to be x minus 25. X minus 25. Okay. So when x is 25, I'm at 0. When x is 25, I'm at 0. When x is, what do I want here? When x is, I'm going to make this 0.25, sorry. Let's make that 0.25. Okay, when x is 0.25, I'm at 0. Okay, and then I'm going to go up by ones. Okay, so 0.25, and then we're going to go up by a slope of 1. Okay. Make this a 45-degree angle. Okay, perfect. This is my supply curve. Okay, there's my supply curve. Okay, so we can call this S of x. Nope, sorry, D of x. This is D of x, that's my demand curve. And then this is S of x, which is my supply curve. Okay, and what I want to know is okay, where is my break-even point? What should my price be so that my supply and demand hit equilibrium? Okay, what should my price be such that, okay, supply and demand, okay, hit equilibrium? Okay, so yeah. Okay, so we could just plug these in. Okay. Set these equal to each other. We've got negative 25x plus 50 is equal to x minus 0.25. Okay. So this is going to be negative 24. Sorry, minus x. This is going to be negative 26x. Okay, so minus an x. Okay, and then we're going to minus a 50. So this is negative 26x is equal to negative 50.25, divide by 26. Okay, and so let's see what we get here. Okay, negative 50. Okay, negative 50. Come on, give me the negative. Negative 50. Okay, divided by negative 20, negative 50 divided by 26. Okay, is negative 1.93, they're saying. I don't know, maybe I didn't do this right. Okay, should have come out to negative 1.93. Okay, but you get the idea. Okay, so, okay, so this would be my price point. No, this is positive. Sorry, this is not negative, this is positive. So this would be my price point. I don't think my graph, I don't think I graphed my graph correctly. Okay, so, but this is my break-even price point, and then if I wanted to know what how many units I would be doing, then I would just plug this Q in. Okay, Q would be X would, and then Q is going to give me my number of units. I think that should be 0.25. But anyway, I kind of screwed this one up, but that's how you do it. Okay, I'm over anyway, so I will let you guys go at this point, and I will see you back here on Thursday. Okay. Okay. Oh, you know where I screwed up? I screwed up right here. This should have been 0.25, and this should have been 25. I reversed them. Huh, my bad. That's where I messed up. So you can convince yourself of this if you want to go back and do that. Okay. Okay. So just rework it out. It works out. Okay. And then this one ends up being $60 and 3,500 units. Okay. So get rid of this gobbledygook.
Would that be your break-even point?
Yeah, this is my break-even point. This is when supply equals demand. Okay, and we could easily see that, again, by just setting them equal to each other. So this would be negative 0.25x plus 50 is equal to x minus 25. Okay, and then we get, this is negative 1.25x is equal to negative 75. Divide, and we get x equals 60. So at $60, okay, this would be not go by those. This would go by 25, 50. These are dollars. Put it at 50, 75, 100. Okay, and so you're going to get your break even to be right here. Okay, at 60, there you go. That makes more sense. 200. Okay. Okay. If you want to think of them as cents, you can just divide everything by 100. Then you would get your break even at 60 cents. You'd still end up with the same number of units, though. Okay. So it really doesn't matter. Okay. Okay, I will see with that. I will see you guys on Thursday. Bye.
Bye.
Thank you.
Thank you, Professor.
Yeah, absolutely.
Thank you, Professor.
Hi, Professor.
Bye.
Professor,
Yes.
this is Adam again. I was wondering if you had like a couple minutes to chat.
Yeah, sure. Absolutely.
Okay, I'll stay on.
Sounds good. Okay, so what did you want to cover? Did I send you the syllabus?
But yeah, so I did. Here, let me hop on.
Let me stop sharing. Okay. Hi.
Hello. Hi. Nice to meet you.
Nice to meet you.
Yeah, thank you for being so accommodating, first off.
Oh, absolutely.
Yeah, no, so I did get the syllabus. I read it over, and the only thing is, so I've been speaking with some of the counselors going back to early July, I believe.
Right.
Trying to get this cleared up. Recently, so basically with all that though, it ended up that they didn't receive, or didn't, my form for my extenuating petition
Right.
received by the person who handles that. So I had to contact the school admissions again directly, and I spoke with a woman named Irma Coronado. And she said that she would try to hand it off quickly to the guy who handles those things.
Okay.
He told me that she understands I can't access Canvas or anything because I can't officially be enrolled in the class yet.
Right. Yes.
And she had told me previously that the turnaround time for those forms is anywhere from 4 to 6 weeks.
Oh my gosh, that's crazy.
Yeah, which is a while. So she told me, I spoke to her again today. She said that they think they could get it done quicker for mine.
Right.
But
Hopefully,
I'm not sure
but
when.
hopefully they meet every week on Monday mornings.
Oh, okay.
So hopefully they can get it done by Monday morning or on Monday.
Yeah, hopefully. So I'm hoping that they can do it ASAP. He was just saying,
Yeah, you're going to have to be enrolled by the first exam. That's the only thing. So,
Okay.
which is September 16th.
okay.
So if you're not enrolled by September 16th, I have to drop you.
Okay. Yeah, no, that's understandable.
But the homework, I can go back and readjust all of the due dates for you for the
Okay.
homework.
Okay.
Okay.
Yeah, and with
So
that,
hopefully you'll be enrolled next week. And maybe I'll give them a call as well this week and just say, hey, what's happening with Adam? Are you getting him enrolled? What's the deal? What's the holdup? And I'll contact admissions and registration
okay.
and just say, hey, he's going to be in the class. Let's try to get him pushed through that he at least has Canvas access.
Yeah. Okay. Well, that would be really helpful.
Okay?
I was just wondering how to move forward in terms of the homework, if you wanted me to just turn it in at a later date, or if there's
Just turn it in at a later date. Yeah.
Okay.
But
So
again, hopefully within a week of us talking now, you'll be enrolled.
yeah. And in terms of accessing what the homework is, even
It's through Canvas, unfortunately.
yeah. So will I just have to complete it once I have access?
Correct.
Okay. All right. Well, I just want to make sure that we're on the same page, and I just appreciate you being accommodating to me because it's been a struggle since registration for me. Just
No, it's
weird
fine.
times, So
Oh, absolutely.
yeah,
Well, it's even when it's not weird times.
yeah, stuff does happen. Yeah.
Stuff happens, exactly.
Yeah. I was at work today. I work at UCI hospital. So I worked 12s and I wasn't sure if I was they let me off early. So I barely made it into the class time too. So that's why I said, thank you for letting me in. But yeah, I'm cutting it close, but I thank you
Sounds
for
good.
getting back to me and everything. And yeah.
Yeah, my pleasure.
Yeah. Well, I look forward to hopefully being in class.
Good. Yeah.
All right.
People like you, I know that aren't going to drop. So.
Yeah. No, definitely.
Okay, I'll talk to you on Thursday.
Well, thank you, sir. You take care. Stay safe. Have a good night.
Okay.
Yeah.